Before the break, we had just started talking about TXY, PXY diagrams and how they relate to phase equilibria. I want to take this moment to just kind of review some of the main variables that we're talking about in a TXY or a PXY diagram. So this is a picture of the system. Imagine it's just a closed cylindrical system with some liquid and some vapor. This is also a point that gets confused a lot, the difference between vapor phase mole fraction and just vapor phase fraction. So I've tried to draw these things to scale and give you real numbers based on the scaling of my diagram. So in my vapor phase, I've got 10 molecules there, and the red molecules are my more volatile component, my blue molecules are my less volatile component. Since I have 7 molecules that are red, 3 molecules that are blue, I would say that my vapor phase of the more volatile component, my mole fraction of the mole fraction of the more volatile component in the vapor phase is 0.7. Likewise, in the liquid phase, I have 5 red molecules, 5 blue molecules. Therefore, my mole fraction of the more volatile component, which is the red, is 0.5. The vapor phase fraction is of the overall everything in the system, liquid and vapor, what percent is one or the other. And I did it based on volume, which isn't really representative probably because vapors take up so much more space than liquids. But just based on volume, the vapor is taking up roughly 60% is what it should say. So 60% of my component is in the vapor phase. Again, just that's based on volume, which isn't necessarily how it happens in real life, but good for visualization purposes. So in this diagram, we'll say P is equal to T1, P is equal to P1, T is equal to T1. Now, if I change either pressure or temperature, all 3 of these variables are going to change. So if I increase the temperature, say, I'm going to have more evaporation that is occurring, and then when it reaches equilibrium again, I would say that my vapor phase fraction has increased. And what happens to the vapor phase mole fraction of the more volatile component? It is probably going to increase if it's an ideal system and there's no azeotropes going on, while the liquid phase mole fraction of the more volatile component would decrease. And that is because more of the, actually it would increase as well, right? Because I'm going to be boiling off some of the less volatile component as well. So in general, for an ideal system, as T increases, or I'll say if T increases, then YA and XA will also increase at different rates, right? So XA is going to increase at a greater rate than YA will. Did I say that right? I have to look at the diagram. Both of them would increase, right? Because I'm boiling off both things. Likewise, if pressure increases, I'm going to get the same thing. So I'm actually going to get different things. Let me finish the thought. If T increases, vapor phase fraction, vapor phase is going to increase because more stuff is going to boil. Whereas if I increase pressure now, I'm going to condense more stuff. So YA and XA are going to go up or down. I had to sit and pause and think about that for a second. They're both going to go down, right? The more volatile component is going to, let me think about it again. Yeah, they're both going to decrease. I'm rusty and I'm having some trouble thinking about this today. If pressure increases, then vapor phase mole fraction, well, that one is easier to think about, right? It's easier to see if I increase the pressure, I'm going to condense more stuff. So the vapor is going to condense into a liquid. But why do the mole fractions go down? Well, the mole fraction in the vapor phase, or in the liquid phase, is going to go down because I'm condensing more stuff. And in general, I'm going to condense more of the less volatile component than the more volatile component. You can see this by looking at the PXY diagram. So that's how I thought about it just now. If I have a PXY diagram that looks like so, right, and say I'm at phase equilibrium at this pressure, so this is P1, then that would mean that my Y1 is there, and my X1 is there. Right, remember how to read these diagrams. Low pressure is the vapor phase region. High pressure is the liquid phase. And if I decrease the pressure now, so let's just pick another pressure. Let's say this is P2. And I have the same overall composition. Got to pick something a little bit higher than that. Say there. Then my Y2 is going to be less than Y1, and my X2 is also going to be less than X1. So that's a great quiz question. I'm automatically going to put that one on the quiz. So if you study that, you'll be okay. All right, where did I want to go next? So you can measure these things experimentally. So let's say we wanted to establish the phase equilibrium behavior for a previously unstudied set of two components. We could set up a TXY diagram, and we could test different temperatures to obtain data points. So if this is an experimental TXY curve, we could vary the temperature and observe the vapor phase mole fractions and liquid phase mole fractions, and we would get data that looks like so. So let's say that's T1, this is T2, T3, so on and so forth. And if our data looks like this, we might say that that approximates an ideal system, because if we connect these data points, or if we model these data points, we'd see that it looks like a nice, smooth, symmetric TXY diagram that we're used to seeing. Now, what happens if we did that same experiment? So this would be for the ideal case, for an ideal system. Also recall what ideal means. So this, I'm not going to say system here, I'm going to say an ideal mixture. Remember that in an ideal mixture, it's distinct from saying an ideal gas or an ideal vapor. In an ideal vapor, there are no interactions between the components. In an ideal mixture, interactions between components are the same as interactions between themselves. Interactions between like molecules. All right, once again, this is for the ideal case. Now, what happens if you do this same experiment and you do not obtain this nice smooth curve? So it's equally as likely, in fact, probably more likely, that when you do this TXY experiment, you would obtain something like the following. So let's say these are your data points that you get. This would then suggest to me that I have an azeotropic system. All right, so now if I connect these data points, and obviously I know what it's supposed to look like, so you would necessarily know how to connect all these data points unless you took a lot of data. And oftentimes when you do an experiment, you take many data points over the whole range. So this would be an azeotropic system. More specifically, a minimum boiling azeotropic system, because the boiling point of the azeotrope, which is there, is less than the pure component boiling points, which are there and there, respectively. Now, I sketched in these red curves because I just kind of traced what the data look like. But in phase equilibria, what we want to do is we want to obtain a mathematical expression that is going to trace these red curves such that for any process conditions that we choose, we can use this mathematical expression and we could obtain or predict what values of x and y we might get. So let's say, for example, I didn't have this red curve, or let's say I traced that red curve and then I fit a mathematical expression. Let's say I wanted to plug this T1 into my system. And T1, and we'll start with an overall composition. I would be able to then, I picked a point that was in between data points that I had. If I had a mathematical model, I could use that mathematical model to predict, this is what I'm talking about, what x and y compositions I would get. For the ideal case, the most common mathematical model is Raoult's law. And there was a video where I talked about the origination of Raoult's law in a little bit more detail. So go back and look at that one. Basically, the main idea is that in Raoult's law, the partial pressure, which is this left-hand term, PA, is equal to the product of the liquid phase mole fraction times the vapor pressure. Essentially what it is the balancing of forces between the, think of it as the pressure exerted by component A in the vapor phase is being balanced by the vapor pressure. Like that's the pressure that the liquid is like exerting, like it wants to evaporate, right? That's how I think of vapor pressure. That's weighted by the liquid phase mole fraction. You can think of that as like the fraction of the surface that this component A occupies. So in an ideal system, everything is additive, which is why we can obtain the mixture property by taking just a weighted average of the pure component properties. So remember, I can also do the same thing for B. I could say 1 minus YA times P is equal to 1 minus XA PB star of T. And remember, of course, this requires that I look up what the vapor pressures of my components A and B, what those are, and that I have either P or T set. In this case, where I'm doing a TXY, I have P set, and I could calculate what my X and Y's are by solving these two equations. Now, my azeotropic system, obviously I cannot use Raoult's law, perhaps not obviously, right? There is no way that I can use Raoult's law to obtain this funky azeotropic shape. So what do I have to do? What is my mathematical model? We're going to spend a lot more time talking about why this is the way it is, but I want to talk about what I call the modified Raoult's law equation. Dr. Sfornos likes to call this the bread and butter equation. He's the only one I know who calls it that, though. But if you ever talk to him and you express that you know what the bread and butter equation is, that'll make me look good because he likes to call it this. The modified Raoult's law is Raoult's law just with a liquid phase activity coefficient. So once again, I'm going to start by showing you what it is, and then we'll talk about why it is later. My brain works best that way when I know kind of the end goal of what I'm trying to get to. All right, so the bread and butter equation is Raoult's law, except there is this gamma, which is the activity coefficient of the liquid phase. So 1 minus YAP is equal to gamma B, 1 minus XA, PB star of T. First observation that you can make is that if you start with the bread and butter equation and you later find out that gamma A is equal to gamma B and is equal to 1, this is going to simplify to Raoult's law and the ideal case. So we'll also have to make a note that these are activity coefficients for A and B. And if you had an accurate model for the activity coefficients, you could theoretically solve this Raoult's law equation in the exact same fashion. So I know what the pressure is. I could then solve for the temperature at each point, and that would give me what my XA and what my YA is. So it's the same exact thing, just this added activity coefficient transforms this nice smooth TXY curve into this azeotropic TXY curve. Now, what are some examples of models for activity coefficients? Once again, I'm going to start by just telling you bluntly what they are, and then we'll worry about where they come from a little bit later. Perhaps the simplest model is the one parameter Margulies equation. In fact, I'm not 100% positive that that's how you pronounce that. I've also heard Margules, but could be wrong. I'm not sure where Margulies was from. I always call it Margulies. Don't get too hung up on pronunciations. Now, in the one parameter Margulies expression, the activity coefficients are described like so. The ln of gamma A is equal to big letter A xb squared, where this A is the one parameter, where the one parameter Margulies model gets its name. Similarly, ln of gamma B is equal to A xa squared. So both activity coefficients are described by a single parameter. A is the one parameter. So that is the number that you must find in order to accurately model the system. Now, with the one parameter Margulies, it is the simplest activity coefficient model, but it has a huge flaw. Maybe you can see what it is already, that it is very symmetric. In other words, a system that is dilute in A will behave the exact same as the system that is dilute in B. So probably not accurate because it assumes symmetry. Assumes symmetry. All right, and then perhaps, obviously, you see that when you plug in this expression for this gamma, you get a nonlinear equation. So if I go to plug in the one parameter Margulies activity coefficients into this model, I'm going to get something that is nonlinear. So another way to write this is A times 1 minus xa squared. Remember, I always like to get the mole fractions in terms of the more volatile component, and then that simplifies the amount of algebra that I have to do. So to rewrite the modified Raoult's laws, in this case, I got YAP is equal to gamma A now, remember, is the exponent of A times 1 minus xa squared. And that is being multiplied by xa pa star of t. All right, so if I know what this A parameter is and I know what the pressure is, then I can proceed forth with solving once I know what the other equation is. So I need two equations still. But if I have a value for this A, then nothing changes. The expression is just a little bit more complicated. I can still go through and solve using the modified Raoult's law to find the bubble point and the dew point curves exactly as I've done in the past. What's this one? This one is exponent of A xa squared 1 minus xb, 1 minus xa pb star of t. All right, so two equations, two unknowns there. Not exactly two unknowns. Remember, you have to set one of xa or ya and solve for the other one, and then also solve for t, which looks very not fun to do by hand in this case. I'm going to introduce one more activity coefficient model. So because of this drawback that it must be accurate, another more commonly used activity coefficient model is the two-parameter Margulies. And as the name implies, instead of one parameter, obviously there's going to be two parameters. See, thermodynamics is not really that difficult once you get the hang of things. Some things are named intuitively. Most things are not, but some things are. So ln of gamma 1 in the two-parameter Margulies is xb squared ab plus 2 aba minus aab. And these are the two parameters, obviously. The two parameters are aab and aba. Some people like to keep the subscripts as 1 and 2 instead of a and b, and that could simplify things. So I'd say A12 here and A21 instead of ABA and AAB. Gets like a little bit of alphabet soup if you do it my way, but I like to call them components A and component B. Times XA there, and then ln of gamma B is equal to XA squared ABA plus 2 AAB minus ABA XP. All right, this looks even less fun to solve. And even more of a reason why I try to teach you that Excel should be almost 100% replacing your calculator at this stage. This is hard enough to do in Excel, by the way, to plug this in without making a mistake. But same thing applies, right? You solve for the expression of the activity coefficient. So I'd take the exponent of both sides and then just plug that into the modified bread and butter equation or the modified Raoult's law equation. We'll do an example of that next time. These videos are running a little bit long. I just want to make one more point, which is if you're not sure what your activity coefficients are, or if you don't know what your parameters are, so if you don't know what A is in the one parameter Margulies, or what ABA or AAB are in the two parameter Margulies, what you could do is take a couple of experimental data points and then fit your data to that model. Oftentimes, this is exactly what people do. So for instance, if I did not know what the parameters are, what I could do is I could run an experiment. I could set up a system, bring it to equilibrium. I could measure the vapor phase and the liquid phase mole fractions. Because I know what the identities of those two components are, I could use the partial pressure, or the vapor pressures, I'm sorry, to fill in some gaps. So I could experimentally measure measuring gamma A and gamma B. Right, and whether I'm doing the one parameter or the two parameter Margulies would inform me of how many data points, the minimum number of data points. Right, so I probably wouldn't want to take just one data point. Although you could do it, you're probably going to have some experimental error though, because no experiment is ever perfect, right? Yeah, I need one data point in order to find the one parameter Margulies, and I need at least two data points in order to fit the two parameter Margulies. More data points are preferable, and then I could set up to take the sum of the least squares. All right, so what I could do is I could say that gamma A is equal to YAP over XA PA star. So I'm just rearranging the equation now. And because, again, I know the identity of component A, so I know what the vapor pressure of component A is. I know what the system pressure is, and I know what the system temperature is because I did the experiment, and then I'd experimentally measure what YA and XA are. And then if this ratio is not 1, that means that I do have an activity coefficient. So that would be how I would measure what the activity coefficient are. And then obviously I could do the same thing for gamma B. It's YBP over XBPB star T. And then once I have values for gamma A and gamma B, then all I have to do is plug them into the activity coefficient models that I have in order to back calculate what these parameters A or AAB and ABA are. And then once I have those, then I can work forwards to figure out what the activity coefficients are for a range of compositions. That's another important point that I wanted to make, is that the activity coefficient is dependent on the composition. It's very important that gamma is not a set value for all values of pressure and temperature. Gamma depends on the composition. So they're going to be changing in general as the composition changes. So that's all for today. Hopefully that is a good reintroduction to where we are, what we're trying to do, and we'll do some practice problems on Wednesday before I get into how we got to all this stuff. So that is all things to come. See you next time.